Today we are going to talk about acids and bases. It's more like we need to understand the historical context of acids and bases to understand how the definition and the understanding of acids and bases has changed over time. Of course, we'll restrict ourselves to just the early 20th century. We won't go for theories that were offered after 1920s for syllabus reasons mainly. So the first idea is that people are just starting to understand chemistry as a subject. People are just starting to identify different elements. And there's this guy in France, uh, Antoine Lavoisier. And Lavoisier is considered the father of modern chemistry. He was the person who first identified oxygen as an element that can be extracted from water and other things. So Lavoisier had a very rigorous technique of identifying different things. And what he figured out was that there are substances that can dissolve in water, and when you do different reactions on them, they give us oxygens. So he was like that, all right, these are acids. They dissolve in water. And he said that when they dissolve in water, they are giving us what we call hydrogen ions. Actually, Lavoisier didn't say that. He was just saying that they have, hello, Vamik. Yeah, that's fine. So he was just saying that we have substances that have oxygen, they give them out, and they're all acids. He did not really know what HCl was. He did not know what HF was. So we can't really blame him for saying that. And then there was this guy after him, Berzelius, who said that, okay, oxygen is there, sure, but acids are always made when non-metals react with oxygen. So he was like that, okay, now oxygen with non-metals makes acid, and oxygen with metals makes base. And Berzelius' theory was true to a large extent, because even now we know that most in fact, metal oxide, they are basic, and non-metal oxides are acidic. Of course, there are neutral oxides, there are amphoteric oxides. So that is the shortcoming of Berzelius theory. But again, you have to understand that we are talking people who were working 200 years back, who didn't even have very high quality glassware or access to even affordable high quality books. So yeah, we have to give them credit for whatever their efforts were. Then in early, I think before 1850s, there was this guy Liebig, the one who designed the condenser, if you remember. So Liebig said that, wait a minute, every acid has hydrogen in it, and we can replace that hydrogen with metal. And this is something we talk about in O levels, when we say that salt is made when you replace hydrogen ion with metal. We say that all the time. Like, you take sodium and you put it in water, you're getting sodium hydroxide. And wait a minute, what you've done is you have replaced the hydrogen ion with sodium metal. So yeah, water is an acid. Similarly, you can do the same thing with HCl and you will get NaCl. So that's again, HCl is an acid. And this also helps us in understanding organic acids like carboxylic acid. So we have Liebig to thank for it. But then came along this guy, and I really loved his name. It's very, I don't know, for some reason, I find this name really cool, Sir Humphrey Davy. And Sir Humphrey Davy was working with, so he helped take this theory forward. And he was like, that, all right, now, initially people thought that acids have oxygen in them. And now there's a major shift. People are now thinking that acids have not oxygen, acidity comes from having hydrogen. And that's a major shift in the way they were thinking about these things. So it's not just oxygen, it's also hydrogen, and primarily hydrogen. And by the way, it's been almost 90 years since the debate started. So it took them 90 years to understand that it's not oxygen, but hydrogen that's responsible for it. So now, hydrogen, first major idea, 1830s. And then comes along this guy, and I think I might Google his image here somewhere. Yep, this guy, Arrhenius. So this person, Swant Arrhenius, he gives us a theory that still holds. He says that basically hydrogen idea is correct, but it's not hydrogen element. It is hydrogen ion. So he said that acid and base, they are related by hydrogen ion, and acid gives hydrogen ion in water, and base accepts, in fact, not just accepts, base gives hydroxide ion in water, gives hydroxide ion in water. So he has given us something that works. And not just that it works, it also helps us in understanding that what happens to water when this happens. Because here's the thing, when water gets H positive, so water is H2O, okay? So H2O. When water gets H positive, it forms H3O positive. If I were to draw its structure, this is what it will look. So oxygen joined with hydrogen like that. This is water. And I've gotten H positive, and H positive is just one hydrogen ion. It has no electrons of its own, just a proton moving around. And now this proton comes in and makes a dative bond with water. And now water has this thing, and a dative bond with another hydrogen positive ion and a lone pair, and this gives water a positive charge. So this is not water anymore, it's hydronium ion, H3O positive. So this makes sense that, okay, we have hydronium ion coming from water, and that is made when you give it H positive. And when you have OH negative, you get the idea of base. Also, this helps us in identifying pH, because what is water? Water has equal amounts of H positive and OH negative. But if so, in water, they're all balanced. But let's suppose there's this balance happening, and suddenly you add a acid to water. So now there's not balance, there's more hydrogen and less hydroxide. So there's an imbalance created. So when there's an imbalance in how water is, there's more H positive, less OH negative. So that gives the water a lower pH value. So when you have equal amounts of H positive and OH negative, you have 7. But the moment you add more H positive, you get hydronium ion, the pH goes below 7. And the moment you add more hydronium ion than H positive, the pH goes above 7. So that's the idea, that when they're equal, it's 7. If you have more of this and less of that, it goes to the right side. If you have more of H positive, less of this, you get the acidic part. But Arrhenius didn't really talk about pH at the time. But the pH idea later on, it was proposed, works with this definition. So acid is anything that gives H positive, base is anything that gives OH negative. And it was really good, because what you can do with it is you can take a litmus paper and you can just dip it in that thing, and you will know whether it's an acid or not. So very convenient. A seventh grade student can do this test, tell us what that thing is, and also have some fun doing it. He got a Nobel Prize for it. And now we have entered 20th century. But there's a problem with this. We always need water to prove something is acid or not. But there are things that behave like acids without water. There are things that behave like bases, like ammonia. And you don't need water to prove that they are basic. Similarly, what about things that are acids like HCl? Arrhenius understands that they're acidic. But what if when they're pure, like pure HCl gas, isn't that acidic? And Arrhenius would argue that it's not, but it does behave like acids. So this theory has that limitation. And like all scientific endeavors, it is open to criticism, open to improvement. And that's the beauty of science, that you can always improve on things. It's falsifiable. So then comes along a pair of scientists, and I'll try to find their image as well. These guys. This is one of them. I bet when you think of chemists, these images don't come to your mind. And this guy, two guys. One of them is Brunstead, okay, like brunch. It's not Braun, it's Brun. And this guy is Laurie. They come up with a very interesting way of looking at the same thing. And this is interesting that you can think of science as very restricted models of things, but actually that's not the case. Science comes from imagination as much as it comes from understanding these principles. They looked at the same idea of acids and bases. I'll just move his image Nicheko as well. They looked at the same thing that Arrhenius was looking at 20 years ago, and they envisioned it as a totally different reaction. They said, okay, Arrhenius says an acid gets to water and it makes H3O positive. But hold on, let's do the same thing now. So if I take HCl and I add it to water, Arrhenius would argue that you have gotten H3O positive. Basically, HCl has given H positive to water, and obviously the chloride ion goes away, it has ionized. But these two guys said, let's look at the same equation, not as acid giving it H positive and making hydronium ion and chloride. Let's look at it as if it's a reversible reaction. If it is a reversible reaction, let me write the opposite reaction. So since it is a reversible reaction, you can add acid to water, you can remove acid from water. It is a reversible reaction. So let's write the reversible reaction. So if you just flip the equation like this, and this is the power of human imagination and looking at the same thing, but from a different perspective, a paradigm shift in things. And this is a very good story for that. And they were like, look at this equation now. I just flipped it, right? Can't we argue that in the equation number one, the equation above, HCl gives H positive to water. And in the second equation, hydronium gives H positive to chloride. We can, right? So what's actually happening is that when acid reacts with something, it does not just give H positive to that. The other thing also accepts that. And all we are doing now is that if this is acid in the forward reaction, this is acid in the backward reaction. And we can say that base is not something that gives OH negative. Base is something that accepts H positive. So in the forward reaction, water is acting as a base. Water is taking that H positive. And in the backward reaction, chloride is acting as a base because it's getting the H positive from a hydronium and making HCl. And yeah, it works. You don't really need water for this. You can do it without water. And most importantly, you can do the same thing with water reacting with itself. Like if I had water reacting with another water molecule, wouldn't this make one water molecule giving the other one H3O positive and becoming OH negative? And yeah, that works. Water is giving us both H positive and OH negative. And Arrhenius theory would say it's both acid and base. It is amphoteric, which water is. But more importantly, water is amphoteric because in the forward reaction, water is giving H positive and accepting H positive. And this one, in the backward reaction, it gives H positive and this accepts H positive. So wait a minute, what is an acid supposed to do? Acid reacts with base to give a different acid and base. And that's remarkable. That is true. Because this is acid, this is acid, this is base, this is base. The only difference is when you have HCl as a solid, it's not acting as an acid because Nothing is there to accept that H positive. But the moment you put it in water, it starts doing that because there is something accepting that which is positive. So HCl is acid from the get-go. And what are acids and bases reactions? They're not in neutralization anymore because Arrhenius said, oh, that's neutralization. That when Arrhenius said that, all right, I have HCl reacting with NaOH. NaOH gives OH negative, so it is base. HCl gives H positive, so it's acid. And when they react, they make this thing. But they said that, hold on, look at it from the other perspective. In the reversible reaction, water is giving H positive to NaCl. And in the reverse reaction, water is the acid and NaCl is the base because NaCl is getting its H positive coming in. It's accepting H positive and making HCl. So while Arrhenius said this is neutralization, they said that neutralization is nothing but making a new acid-base pair that exists in solution form. And turns out it doesn't always have to be in solution form. This solved a lot of problems. For example, Arrhenius had no idea why ammonia would be a base. But with this theory, it works because let's say I take ammonia, I add it to water. Now what happens here? Ammonia makes ammonium ion and hydroxide ion. Okay. Now why is that true? That is true because if you look at the left side and the right side, ammonia here has 3H and over here it has gotten an extra H positive, takes H positive, and this gives H positive. So it does not like cancel out Arrhenius theory because Arrhenius said, oh, wait a minute, ammonia is what? Ammonia is base because it gives H OH negative, although it didn't have any OH negative to begin with. But they said that way that is because water is an acid and water is acting as an acid with ammonia. So when water gives H positive to ammonia, ammonia becomes ammonium, and that ammonium is acid because in the reverse direction, if you look at it, in the reverse direction, ammonium loses an H positive. So it gives H positive in the reverse direction, and this takes H positive. So hydroxide itself, well, Arrhenius was saying they give hydroxide and that's why they're base. They're saying they're base because hydroxide itself accepts H positive. But then he was like, wait a minute, guys, you have gotten me so confused with this. This also gives H positive. That also gives H positive. Which one is acid in reality? They're like, they're both acids, but okay, we'll give you a different name. So instead of calling all of them acids and bases and acids and bases, that one acid reacts with a base to make another acid and a base, let's just give them a different name. So they said that the things that exist in the solution form and the things that you get at the end, we will call them conjugates. So this one is acid, but this is conjugate acid. And that one is base, but it is conjugate base. So this thing is acid, and that is also acid, but this one is conjugate acid and conjugate base. So what's an acid and base? When they react together and they do neutralization reaction, they're basically giving you conjugate acid and conjugate base. And this allowed us to compare things that were acids because everything that is acidic can be broken down to become base if it's reacting with something that is stronger acid. And that tells us that, wait a minute, pH isn't always 1, 2, 3, 4. It can actually be in 1.1 and 1.7 and all of that. Why? Because it's just a comparison thing. HCl is acid in water because HCl is a more acidic thing, water is less acidic thing. So when HCl is added to water, HCl starts acting as an acid and water starts acting as a base. But that same water, when you put it with ammonia, water is more acidic than ammonia is. We don't say that ammonia is more basic than water. We can also say that water is more acidic than ammonia, which means that now water gets to lose its H positive and water does that with ammonia. So ammonia becomes base, it accepts that H positive and water becomes acid. So that is the amphoteric nature of water. And this was remarkable, like just looking at it. And it also helped us work with things that weren't really acidic to begin with. Like they didn't even have H positive to begin with. For example, there's this thing called what was its name? I'm forgetting the name, but the formula is C6H5N. So, sorry, C5H5N. So C5H5N, and if I react it with water, it forms C5H5NH ion with hydroxide ion. And this is a base. And this is a base because water is an acid. So water gives H positive. So I'm going to call that acid. So what is the acid here? What is the acid here? And this is the base here. And this is the conjugate acid because this is formed from the base. It has accepted H positive. So on the way back, it's going to lose that H positive. And this is the conjugate base. So that's what it is. It also tells us about many different organic compounds. And then comes along one of the most brilliant minds in chemistry ever. This is a guy whose students have won more Nobel Prizes than any other teacher in the world. Uh, he comes from that college, what is it called? Uh, UC Berkeley. Uh, his students, I think 7 or 8 of his students got Nobel Prizes. That's insane. And he himself was uh, nominated for Nobel Prize 41 times. 41 times. And this is, let me Google his picture. This guy. His name is Louis. Gilbert Louis. Just to give you an idea of what you've worked with that comes from Louis, he was the guy who gave us the idea of covalent bond, of dot and cross diagram, of valence electrons, of isotopes, of acids and bases, of thermodynamics, like all the energetics that we have studied. Just a few of his works, by the way. Insane. Octet rule. वो इस बने दिया था मैं. And he's the guy who named photons, like the particles of light. So this guy has like major mega mind. Okay, so what does Louis say? Louis is like, wait a minute, guys. I know you are obsessed with hydrogen for 200 years now, and you think that hydrogen has this special quality that makes things acidic and makes things basic, but you guys are missing something out. You guys are not looking at what exactly is it in H positive that makes anything act as an acid. The problem with H positive is it does not have any electrons, and it has just one first shell of electrons that it needs to fill up, and it becomes stable. The only reason things with H positive are clinging on to other things is because hydrogen ion craves electron pairs. Hydrogen ion is a proton which has one empty electron shell in the first one. It can have 2 electrons. So whenever it sees 2 electrons, it just jumps onto it. And I remember that he said that if you were saying that acids are things with a hydrogen ion, you might as well say that things that are oxidizing agents are things with oxygen, which we know is not true, right? So that's what he said. So what does Louis say? He says hydrogen ion is looking for a pair of electrons. So basically, acid just looks for a pair of electrons. So it accepts electron pair, and base gives electron pair. And that's remarkable because now all of those things that were being left out by these theories, they start to make sense. And not just that, they also start to make sense in terms of electron pairs. Because why is hydrogen ion over here, why is this one reacting with water in the first place? Because water has this thing it really loves, electron pairs. And do you notice that water is giving an electron pair to hydrogen ion? It is making a data bond with it, and it works every single time. OH minus has electron pairs that it gives to H positive, which is why bases are OH minus. things with OH minus are bases because they have electron pairs to donate. And nitrogen has 5 electrons, right? Look at ammonia structure. Ammonia is like this. This is ammonia, right? Look at this beautiful pair of electron right there. Why wouldn't it act like a base? It would. Because H positive को ये 2 इलेक्ट्रॉन नजर आने उसने भाग के आ जाना है उससे वो लेने के लिए. So ammonia is basic not because it's giving OH negative from water or ammonia tries to like accept H positive anywhere it finds it. It is because H positive itself craves electron pairs. And that basically the power of this theory is that now there's only 2 types of chemical reactions. The whole chemistry makes sense now. What are chemical reactions? There are reactions in which individual electrons are transferred. What's happening here? Individual electrons, they are the ones coming and going, which we call redox reactions. And there are reactions in which pairs of electrons are coming and going. And those we call acid-base reactions. And I dare you go find a third kind of chemical reaction. If you do, let me know. We'll share some prize or something. Of course, the debate doesn't end there. There are this is the most complete theory we have right now. But because we don't really need water for this, we don't need things that don't have H positive in them to act as acids. Because why is carbon dioxide acidic? Because it has lone pairs to give away. It doesn't have any H positive. It doesn't need H positive. Why is nitrogen dioxide acidic? Why is sulfur dioxide acidic? Why is sulfur trioxide acidic? All of those things are acidic because they have lone pairs that they try to accept. And why is copper oxide basic or magnesium oxide basic? Because it has lone pairs to donate. Why is कौन सा आयन था वो? Peroxidized sulfate. Why is that a base? Oh, sorry, why is that an acid? Peroxidized sulfate is an acid because it accepts H positive. Oh, sorry, it accepts lone pair whenever it finds it. There is a Russian guy who worked on it later on, and he said that actually wherever there is 2 electrons being exchanged, or he also tried to define acids and bases in terms of sulfur, because there are some sulfur species that at first glance are difficult to classify as Lewis acid or Lewis base. I think his name was Usanovich. That is even more complete theory than this one, Lewis. But because Lewis was American, his theory has stuck. So Usanovich, uski theory itni zyada abhi nahi hui. So maybe sometime in the future, people will accept his theory as well. He was I don't know, usko Nobel Prize diya tha ki nahi diya tha. So there are many theories, but because theory is something that explains a set of behavior, a set of chemical reactions, a set of scientific phenomena, and so far we have to focus on 3 theories. So just to give you a review, initially, most basic level, we saw Arrhenius saying in water, acid gives H positive, base gives OH negative. This is good for basic acids, for basic bases, sodium hydroxide, nitric acid, sulfuric acid. It's good for that. And we are working with strong acids, strong bases. But then weak bases are difficult to explain using this. So Bronsted and Laurie come in and they say that actually acid and base react to make another acid and base pair, which is conjugate acid, conjugate base. And that is because one of them gives H positive to the other one. So any acid-base reaction is a transfer of H positive ion. And it's interesting because पूरी chemistry में हम इसको कैसा सोचते थे? हम सोचते थे chemistry में electrons involved होते हैं और chemical reactions में electron आगे पीछे होते हैं. But this was a case in which it's not electron, it's H positive going away. And wait a minute, what is H positive? Tell me, what is H positive? What is it made of at the atomic level? A proton, yes. So this is the first of its kind chemical reaction where a proton is being given and a proton is being accepted. And then comes along Louis and he says that it's actually, we are going back to electrons because it is pairs of electrons which are being given by the base and accepted by the acid. And that is the most complete theory in our syllabus. Of course, the even better one or even more complete one is the one by Usanovich, which just talks about negative and positive ions. I love that theory, by the way. लेकिन हम उसको नहीं देखेंगे अभी के लिए. Okay.